Welcome back to Nick's Algebraics. Today we're going to talk about momentum, impulse, and collisions. So with me today we have Random Guy
It's good to be back.
and we have Dubious Guy.
Hello, everyone.
Before I start talking about momentum, let's revisit Newton's second law. So remember, Newton's second law says that the net force equals ma. How does acceleration relate to velocity?
It's the derivative in respect to time.
Yeah, good. So A is just dv dt. M is a constant. I can bring it inside the derivative. So the right-hand side will be the derivative with respect to time of mv. So the product of the particle's mass and velocity is called the linear momentum of the particle. And the symbol for that is p. So this is equal to dp dt. And let me just write here that momentum is mv. So keep in mind that momentum is a vector quantity with the same direction as the particle's velocity. So this right here is basically Newton's second law in terms of momentum. So this is the form in which Newton originally stated his second law. So it wasn't originally F equals ma. Okay, next up is impulse. From earlier, I know that the net external force equals the derivative of momentum. I can do something very physicsy. I'm going to multiply both sides by dt. I'm going to integrate the left-hand side from t1 to t2. So I'm going to get this. And what's the right-hand side going to equal if I integrate it from p1 to p2?
Delta P.
Just to be very explicit about it, it's p2 minus p1. So this p2 minus p1, that's the change in momentum. So just like Dubious Guy said, I can write that as delta p. And this is called the impulse. So the symbol for impulse is capital J, and it's also a vector quantity. This has a special name to it. It's called the impulse momentum theorem. All right, so this is the impulse momentum theorem. It says that the impulse of the net external force on a particle during a time interval equals the change in momentum of that particle during that interval. All right, so it's analogous to the work energy theorem. Remember, the total work is a change in kinetic energy. Looks pretty similar to that. All right, and this also equals the time integral of the net external force. So this is for a general net external force. It can be either varying or constant. But if you don't know how the force varies with time, but you do know the average force and the duration of the collision, then you can write the impulse equation another way. I'm going to multiply and divide by t2 minus t1. So divide by t2 minus t1 and multiply by t2 minus t1. So what does this look like right here from calculus?
Pretty average.
Yes, it looks like the average value of a function. I can just say that this right here is f average.
So that random thing we learned in Calc 1 that never showed up again has a use.
Absolutely. And this t2 minus t1, I'm just going to write as delta t. So now let's do an example.
A 45-gram ball is dropped from the height of 2.5 meters onto the floor. The ball bounces to a height of 1.9 meters. Calculate the impulse delivered to the ball during the impact.
We want to find the impulse. We know from the impulse momentum theorem that J equals delta P. And I'm using magnitudes right now. So if we want to find the impulse, we need the change in momentum. We have a ball being dropped, so let me break this up into different times. Initially, the ball is at rest and it's at a height of 2.5 meters. So I'm going to call that y1 equals 2.5 meters. So this is 1. And also the ball is initially at rest, so v1 equals 0 meters per second. Then the next thing I'm going to call 2. So then the ball drops, and just before it hits the floor, I'm going to call that 2, like I said, and the velocity is going to be v2, which we don't know. And then 3 is going to be after the ball hits the floor and it just starts to go upward. So that velocity, which I don't know yet, is v3. And then lastly, 4 is when the ball comes back up, but this time it's at a height of 1.9 meters. So I'll call that y4 equals 1.9 meters. And what's the velocity at this time?
Should be 0.
Yeah, 0, because it just reached its max height after bouncing. So we mostly care about 2 and 3 right here because we're trying to figure out the impulse delivered during the impact. So 2 and 3 is before and after the impact. So for the change in momentum, remember momentum's mv. So we're doing final momentum, so mv3 minus the initial momentum, so mv2. So we know m is 45 grams, but we don't know v2 and v3. So how are we gonna figure out what v2 and v3 are?
Using energy.
Yes, that's one way we can use energy.
For kinematics.
I'll mention that in a second too. So to find V2, we have to look at 1 to 2. So if we use energy, let's look at the different kinds of energy that are involved from 1 to 2. At 1, there's gravitational potential energy. So I'm going to call that UG1. And the ball is at rest, so there's no kinetic energy, there's no springs, so there's no elastic potential energy. So all we got is gravitational potential energy at 1. And at 2, the ball is basically at the floor, so there's no more gravitational potential energy because it's at y equals 0. But we have kinetic energy. So all the potential energy is going to be transformed to kinetic energy. So I'm going to call that K2. All right. So UG1, that's just MGY1, and K2, that's 1 half MV2 squared. So the M's cancel because I can divide both sides by M. And I want V2. So I'm going to multiply both sides by 2 and take the square root. And remember, when you take the square root of both sides of an equation, you have to put plus or minus. And I'm actually going to use minus because V2 is downward. I didn't say this yet, but I'm defining up as the positive y direction. So this is the negative square root of 2g y1. I could have used kinematics also. Like I could have used v squared y equals v squared initial y plus 2a delta y. All right, and then it's the same idea for finding v3. Initially, it's all kinetic energy. So K3 equals, and then at 4, it's all gravitational potential energy because the velocity is 0. So equals UG4. So K3 is 1 half MV3 squared, and UG4 is MGY4. So just like last time, the masses cancel. And to find V3, I'm going to multiply both sides by 2 and take the square root. So you're going to get this. And I'm doing the positive square root because V3 is upward, which is in the positive direction. So now I have V2 and V3, so I just gotta plug that into this impulse equation. So I'll factor out the m, and V3 is the square root of 2g y4, and v2 is negative square root of 2g y1. So we have a double negative, so it's going to become plus square root of 2g y1. And I can start plugging things in, but let me actually factor out the square root of 2g just to make it a little easier. So now let's plug everything in. So the mass is what?
Given.
Yes, it's given. It's right here, but it's in grams.
I
Yeah.
like kilograms.
Yeah, so let's convert this to kilograms. So I just have to move the decimal point back 3. So you get 0.045 kilograms. And I'll just ignore the units. And G is 9.81, so we have times the square root of 2 times 9.81. Y4 is 1.9 meters, and Y1 is 2.5 meters. Okay, so if you put this all in your calculator, you're going to get that the impulse delivered during the impact is about 0.590. And the units are kilograms meters per second because mass is in kilograms and velocities in meters per second. So it's kilograms meters per second. Part B, if the ball is in contact with the floor for 1.5 milliseconds, find the average force on the ball during impact. Average force, we have an equation with average force in it right here. The impulse is just the average force times the time interval. So I'm going to use magnitudes here. So J equals F average times delta T. So we want average force, so I'm going to divide both sides by delta T. So you get J over delta T. So J, we know that from part A, it's 0.590. I'm going to keep one more digit just so we don't have any rounding issues. So instead of 590, I'm going to say 5899 kilograms meters per second. And the time interval is 1.5 milliseconds. So I'm going to convert that to seconds. So I just have to move the decimal point back 3. So you get 0.00150 seconds. And just looking at the units, this is going to be kilograms meters per second squared, which is newtons. So if you put this in your calculator, you get that F average is about 393 newtons.